Hi, welcome back. So I hope you were not too annoyed by the previous lecture that was a little long, but this one is going to be shorter, I promise. Um, so today, in this lecture, we are going to talk about using energy as a concept to write equations of motion for our mechanical systems. It is in some cases easier to work with energy rather than Newton's equations of motion. We'll see how it works. But before getting into the method, maybe it's a good idea to um, take a look at the basic concepts, mostly as a reminder what they are. So a few terminology and concepts. The first one we are working with is work. And all of these were covered in physics and dynamics classes. I'm just very quickly reiterating them for the sake of completeness. So work is any force that moves, can potentially do work. So if you have a force that is acting somewhere, and that the place of activation of the force is moving, the force may do work. And the definition of work, let's use notation W. Sometimes people use U. Let's for now use W. Is the integral of F dot dr. So somewhere along the way, this is my force. Maybe it has rotated. R is the vector from a reference point to the point of application of force. This is R1. This is R2, the final position. And taking this integral from R1 to R2 gives me the amount of work this force is doing during this motion. So it starts here, maybe it rotates and moves to that point. This is work. Because there is dot product, means either the force, the component of the force along the movement, or the force multiplied by the component of displacement along the force. Either way, they both work the same way. If the force and displacement are in the same direction, so this is force and I'm moving this way, the dot product just becomes a regular product. If the force is perpendicular to the direction of movement, so I go this way and I'm pushing that way, because they are perpendicular, the work is going to be 0. So that's work. So a few components that we have seen before. For instance, if we have a spring that is being stretched in some direction, the force is pulling it, so the work of this force is the integral from some initial point to some final point, x1 to x2 of f, which is kx times dx. And imagine if it is being stretched, force and displacement are in the same direction, so that is positive. And this turns into the famous equation we had, x2 squared minus x1 squared. And whatever work the force F is doing is being stored as a potential energy in the spring. Or the work of gravity, when we have an object relative to ground, This is work of gravity, force of gravity. And moving from some original height from y0 or y1 to y2. Work of gravity is integral from y1 to y2 of, it is mg dot, the dot product, dr, because now mg is the opposite direction of movement. It's going to be minus mg dy, which in this case is minus mg y2 minus y1. And so maybe I could have put it the other way to make it simpler. Anyways, if you assume another force was here pulling it up, the amount of that force would be mg, assuming constant velocity. It would be mg positive, this one would be positive, and the work of this force that is pulling it up will be stored as potential energy in the object. Cool. That's work. What else do I have? Next, we have already talked about energy, but let's look at it again. Energy is, I don't like this definition, but it is, I think, that the definition, ability to do work. That is the definition of energy. And there are different forms of energy in the mechanical context. We have kinetic energy that we talked about in translational domain. Kinetic energy is usually shown with T equals a half m. Let's put it as x dot. X dot squared in rotational. T is a half j theta dot squared. We already talked a little here, but potential energy, the elements that store potential energy, and we work mostly in this course, are a linear spring, which has potential energy. We show it as U equals a half k x squared minus x naught squared. Similarly, in its rotational component, a half k theta squared minus theta naught squared. And we also have gravitational potential energy. Gravity, where U, let's put it US, let's call this UG, is mg y minus y naught, and y naught is any arbitrary reference point we can choose. So let's maybe quickly look at these. if you recall from the dynamics course, any force that is conservative has a potential energy. These are the two examples of potential energy. Conservative forces that have potential energy. Conservative forces. And if you have an element that can store potential energy and applies conservative forces, that element does not dissipate energy and keeps the total energy of the system, total mechanical energy of the system constant. The next item on the list is work energy principle. Work energy principle. And essentially, if you have your system at kinetic energy 1 and you do a certain amount of work on the system that is a combination of all the forces, all the external forces acting on it that do work, the summation of all those works, and your system ends up in a different state that has a different kinetic energy T2. This is the work energy principle. In other words, the change in kinetic energy equals the amount of work done by external forces. External forces? No, not external forces. All forces acting on it, acting on the system. I want to conserve, speaking of conservative forces, I want to conserve my space, so I erase this. Now I have more space to do here, some additional writing. Where was it? And the last piece that could be, no, two more things. So this work energy principle is universal. Doesn't matter what forces are acting within or on the system. It could be conservative, non-conservative, or any other force. This always holds. If you only have conservative forces within the system, there is no non-conservative force, the energy of the system remains conserved. So that is conservation of mechanical energy if all forces are conservative. So essentially in this case, this W will be the work of all conservative forces, which we saw here means the works are stored as potential energy. So in this case, total energy of T plus U in one state equals total energy T plus U in the final state. And then that is the total energy of the system. And the last bit of terminology or concepts, the concept of power. Power is defined, let's call it with P, is defined as the rate of change of energy, E dot. Or thinking work as another form of energy equals W dot. Rate of change of work or energy is power. And going back to that definition, if you take derivative with respect to time, you end up with FDR and FdV, sorry. So power is F instantaneous power, F dot D, let me call it X dot or dot V, what do I call it? Let's call it X dot. Also in a rotational domain, you could have tau dot, why do I have D here? F dot X dot, F dot theta dot. Maybe vector here is a little redundant because we only work with rotation about a fixed axis, and these are always going to be along the same axis. But it also it has the potential to compactly show whether they are in the same direction or the opposite direction. So that is power. So these are all the basic terminology and concepts in relation to energy. Let me clean up the board and we can see how we use them to find the equations of motion for a mechanical system using this method. Alright, so the best way to see how we can use energy to get equations of motion for a system is to see it in action. So here I have again a very basic example of my mass moving horizontally, and there is a spring with assuming resting length equal to 0. We want to solve the system using energy method. So at some point, some arbitrary time that is shown here, my mass is at some distance x and it is moving with some velocity x dot. Assume both of them in the positive direction so we don't mess up the signs. Here in this particular instant, the kinetic energy is a half mx dot squared, and the potential energy, I only have one element that stores potential energy, is a half k, it's x squared minus x naught squared, which we assume is 0, x squared. So these are I only have one element that can have inertia, kinetic energy, that is this inertia, and only one element that can have potential energy, that's this spring. This is K. So my total energy is a half times m x dot squared plus k x squared. Because there is only conservative forces here, the total energy of the system remains constant, which means it doesn't change with time. That is dE over dt, the rate of change of it is 0. Now if I take the derivative of this with respect to time, I will have this a half cancels with both of those, so I'll have m x dot. It's going to be 2m x dot times derivative of that, which is going to x double dot, plus kx x dot equals 0. So one condition could be that x dot equals 0. That is, the system stays still. That's not a fun solution. So for this equation to work always, I can factor out one x dot. What we are remaining with, let me put it this way, x dot mx double dot plus kx dot equals 0. If x dot is not 0, I can cancel it, and I'm left with mx double dot plus kx dot equals 0. And this is the same equation that we had derived before, maybe 2 lectures ago, or last lecture too. So you see, it was a little maybe easier because we didn't have to worry too much about the direction of force. Is it positive? Is it negative? And in some way it is easier. And it came directly from the balance of energies, which to me at least is a lot more intuitive than equations of motion using Newton's equation. So this was a condition that we didn't have any non-conservative force. Make this a little nicer. Not much better. Let's do the same example, but let's now have a damper here with damping B. This is the conservative case. Conservative. This is the non-conservative. When B was 0, B is not 0. So what do we do? Still at this instant shown, the kinetic energy is like that, and the potential energy is like that, and the total energy is like that. However, the total energy does not remain conserved. So the rate of change of energy of the system equals to whatever energy is being taken out from the system. And that is what this damping element is doing. This is the power of damper. The rate of change is power, and that is the power of the damping force. And if you recall from before wiping this, power is F dot, not D. Why do I write D? F dot x dot, but these are in vector form. So now this becomes a little, maybe you need to be careful about the signs. If x dot is positive, the force of damper, I'm yanking this forward, and the damper is going to resist it in the opposite direction. So this is going to be minus Fd, let's give it name, x dot, and Fd is Bx dot itself. So this whole thing, E dot equals Bx dot. That's a big dot, x dot. So I had calculated E dot here, so I'm just going to reuse that. X dot times mx double dot. Oh, this is going to be squared because I have one x dot here, one x dot there, plus k x dot equals this power of damping, which is b x dot squared. Again, same condition. If x dot is 0, not a good solution for us. So pretending that x dot is not 0, I can cancel this, and I'm left with mx double dot. This is also, it needs a minus here too, minus minus. Plus, now this comes to the other side, becomes bx dot plus kx. Why do I make so many mistakes? Equals 0. And this is the equations of motion we arrived last time when a system has a damping. Same way, you could also have, for instance, input forces, and this input force may, depending on its value and direction, has a power and may add or remove energy from the system. You can do it, you can include it in the equation the same way, and you would arrive at whatever equations of motion that the system has. So this is the energy method. It's a little, how do I say it? Basic or rudimentary. Although we do not get into any detail, and I don't intend to use it, this is a kind of a special case or a short version of what is called Lagrangian mechanics. So Lagrange, my PhD advisor was saying, I don't know, I haven't read his book, but he came out a few years after Newton, and Newton was always drawing this free body diagrams and everything. Lagrange wrote the entire book about Lagrangian mechanics without a single figure in the entire book. So no free body diagram involved. And you can do a lot with Lagrange equations instead of Newton's equation. So there is a thing. This is, I'm just showing it and we move on. We don't have to worry too much about it. We are not going to use it. There is a thing we call Lagrangian, L, that is equal to T minus U, kinetic energy minus potential energy of the entire system. And imagine you have a bunch of degrees of freedom. Your system has a lot of degrees of freedom. Each of those individual variables that describe the system, if you call them, well, DOF, we show them by variables Q. This is the standard notation. Then the equations of motion takes this form, this partial derivative of L with respect to Qi minus time derivative of partial L partial Q dot equals 0. This equation defines Lagrangian mechanics. It's an alternative way to arrive to the same equations of motion as Newton's equations of motion, but using the concepts of energy. If you expand this, you arrive to something similar to this, but because now our degrees of freedom could be arbitrary, could be any one of the sets that describe the system, you will end up with these additional terms that are now taken care of by this slightly larger and more complex equation. So I just wanted to mention that Lagrangian is based on energy method, or it's the general form of energy method to drive equations of motion. And yeah, that's all I have for this lecture. As I told you, it was a much shorter lecture. I hope you enjoyed it, and I'll see you in the next video.